Before we get into today's lecture, I just want to make a comment about the hormone number 1. Okay? I looked at you guys' hormone number 1. Now, it turns out the kinematics you assume for this simple single degree freedom problem, depending upon what you emphasize, you could have a different coordinate system, different assumption. And in this case, as the ground is moving, you gotta remember when the ground is shifting, the ground rules also change. So this problem, even though it's a single degree freedom problem, it's not as simple as what you think. And let me explain why. So we have here mass, we have here spring, and we have here ground is oscillating. Okay? Now, there are two ways you can come up with the kinematics. One is I will call stiffness dominated. The other one I will call mass dominated. The reason I want to take some time here is, even though we are dealing with the single degree freedom problem, when it comes to physics, if we understand all the ins and outs, you can use a single degree freedom problem to a tremendous advantage in your physical insight. Okay? In the stiffness dominated cases, this is huge, okay? Huge ground. You know, you can use it just huge like that, okay? Or it can be just a simple shape on the road condition. When this ground moves a little bit, relatively at that instant, the force of, say, is so big, okay? So this guy, therefore, when you move this guy move instantaneously about that way. Okay? So that the distance here is still, say, if this is h, this will still be the h. And then you might have a real displacement from here to there, which I will call y. So if I take, say, inertial coordinate origin over here, okay, the absolute displacement over here would be h minus, say, t plus y, okay? That is so this guy, then from there, it'll come down static displacement, which I will call T static. And then y will be measured from here to there. Okay? So now, because of that, what happens here is from there, that distance, okay, is h minus yg. And because so if I write down the free body diagram, here's what happens. Okay, I have same mg. I have same k, y, this total y, minus ts. So I'm over here. And then spring is squeezed about that much. So we have to take that one. And then the absolute acceleration is my double dot, which is, is there eraser somewhere? Which one is erased? Is that erased? Okay. Let me get rid of that. Which is simply my double dot. Okay? So this is what's happening when stiffness dominated cases. Now, when the mass dominated cases, what happened is, yeah.
Same as YG in your drawing?
No, this ds is this one is a static force. Okay. In the mass dominated cases, this is the other way around. This becomes the other way around. In other words, when ground moves, the stiffness is so soft, it'll just squeeze in. Okay? It'll not go up like this. Okay? This guy will not move in the same way this guy moves up. Okay? So in that case, what happens here is we have the following. That is, when there's this motion, this guy will not go up, this guy will not, you guys use the word budge. I'm not going to budge, right? When somebody's pushing you. So this mass doesn't really move. So what it does here is, when this guy moves like that, this is ground, all that does is squeeze a spring like this from here. And then from here, we have static displacement. And then we have total displacement. So this is y. This is Ts, and this is that. So what that does here is, in the free body diagram over here is, this is same as before. Is simply that. Okay? And the difference there is, let me just, So in this case, the total y is from here to there. If I take that as origin, so that's just simply h minus ds plus y. Now, let me see what. Okay, I think I made a mistake here. If I measure y from here, I have h, and h is from here to there, from here to there. Just a minute. Let me rewrite this guy. Maybe I may have confused you. Okay, let me start all over again. Let me just do. I'm sorry. Let me just do one at a time. So I was trying to do two at a split to contrast. Obviously, that I got confused myself. So this is origin. Now, when I push this guy about that, and so this guy go up like that because the spring is so stiff. So that was H. And so is this guy, is H. Okay? So from here to there is now H plus YG. From that, I take down to here, which is a TS. And from here, I go up new position, which is a Y from here. So if I take a total kinematics, then this is H plus YG from here to there, then minus ds plus y. Now I feel much better. Okay? So that absolute acceleration is YG plus y double dot. Okay? Which is what I posted it. Then the delta y that goes on the spring, with all the things done, this guy is really y minus yst is really the actual spring distance changes. Okay? So what that does here is in the free body diagram, I have mg, okay? And I have say spring force is minus k delta y, which is minus k y minus yst. And the inertia force is this guy times mass. I'm sorry, inertia force is not that way. This way, I'm sorry. Is m yg plus y double dot. So the net equation is my double dot plus ky is equal, if there was a force acting on it, on the mass, I have that, and plus minus, because that was a plus myg double dot. Now, this one is very important because when something like a high rise is subject to the ground excitation, like earthquake, it's the earthquake, the ground acceleration, and the mass will act on that structure. This is a tremendous acceleration force. Okay? That's why buildings collapse during the earthquake. And this is more realistic because the stiffness of the usual bridges and buildings are much, much stiffer. I mean, you design to be stiff, okay? So that this is a stiffness dominated. Okay? Now, for mass dominated, which was what I was doing, it turns out, nothing happens when you push this guy, because the stiffness is so soft. When I push this one, this guy is still there. Okay? Because it's the mass is much relative. It's all relative. Much bigger than the stiffness. So it's still there. Then from there, it comes down and up y. And the free body diagram over there is mg k. The distance over here is from here to there. Subtract out the actual length. That makes yg minus ts. And the acceleration is simply my double dot. So in this case, what happens here is my double dot plus ky equal to kyg. Okay? This is mass dominated. The one that we just did, this stiffness dominated cases, we have my plus ky equal to minus myg double dot. So if you ride on bicycle where bicycle tire is very soft, you ride on the groovy places, this is more appropriate model. If you put the maximum air so that the tire will just bump over, this is more of the appropriate model, even for the same physical system. Okay? So appreciating this, of course, in truth, it's somewhere in between. Okay? So somewhere in between is, if this is 1 and 2, 1 times alpha plus 2 times 1 minus alpha, where alpha is 0 to 1. Then what happens here is my double dot plus ky equal alpha k yg minus 1 minus alpha m yg double dot. So this is a little bit more realistic model. Okay? So you see there's more way to look at single degree freedom problem for accommodating the different physics. Any question? Yeah.
What does the alpha represent again in the last
The weighting. It's just the weight.
Oh, okay.
Sorry. Yeah. So if it's purely stiffness proportional cases, then set alpha equal to 0, which indicates that we will study about mass dominated, stiff dominated later on in the vibration. The frequency spectrums have, when you measure a certain system, plot the frequency response function, you can tell whether the system is mass dominated or stiffness dominated also. We are not there yet. That's why I'm just using arm waving. When stiffness force is magnitude bigger than, there's a precise way of defining that. Okay? So what it is it's nice to know how far you can push with the single degree freedom. This becomes much more relevant for nonlinear problem because you cannot really solve it, or you can solve it, but you cannot really handle physics of a very complex nonlinear problem with the million degree freedom. It's just not possible. Okay? And there's a saying for that. The Native Americans has a saying something like, I can count the 5 with the one finger. I can count another 5 by another finger. Then I don't know how to count. Okay? The Western men and women, when they heard this story, they thought, they are so ignorant, they can't even count 11, 12, 13. But there's a truth. That is, humans can comprehend something simple. Okay? Okay, now let's start today's lecture. So what we're going to do today is apply Hamilton's principle and derive Euler-Lagrange equation for the continuum. And continuum, if you took mechanics course, what was it? MCEN what? I kept, what?
Yeah,
5022020?
23.
23.
23?
Yeah.
Okay. So we are one step down, 5022. So if you took that course, I trust most of you took, you spend considerable amount of time on continuum, okay? Equilibrium, the elasticity equation, whatnot. Okay, the continuum bar is the simplest possible equation you probably have learned, okay? It's a simple equation. But to derive the dynamics equation or continuum bar, we are often led to believe, just throw in the density times acceleration, right, as inertial force. That's good. Now suppose that you have not only continuum, there's a little spring. And then you are required to write equations of motion. It's not as simple as what you think. And this is where the Hamilton's principle is quite useful. Of course, you can derive this equation using Newton's law or D'Alembert principle. So I thought that to reinforce the basic concept of Hamilton's principle, we go over one example where it's a good thing to review what you studied the previous semester too. Some of the things we're going to talk about, you learned in the previous semester. Or for those of you who are, how do I do that? No? I forgot. Okay. All right. So first what we do here is we work with kinetic energy. Okay? Kinetic energy. Kinetic energy is given by that. So do I need to go over why I got this? Everybody knows, right? It's just mass times velocity square integrating over domain. This is what the difference between continuum and discrete. In discrete case, you have only one mass. In continuum case, you have a mass distributed. So there's a small mass, small mass, small mass, small mass, small mass. You have to add all of that. And every location, you have to have a dm times v square. And you have to add them up. And you have to integrate that over volume. And if I take a mass, this mass is not the usual mass, since this guy is dm v square half, okay, entire domain. So this guy is a mass per unit length. So this guy is a kilogram per unit length. Okay, per meter, I'm sorry. This is mass per unit length. Okay? It's not the density. No, it's not the total kilogram. The potential energy is EA, because sigma is epsilon, E epsilon, epsilon. So half of that is half of that is half E. Epsilon is du over dx. Okay? And square is a square. So when you integrate again over dv, you have area at each cross section over here. Area might vary. And then, in other words, dv is area, which is function of length, dx. Okay? Now, don't be shy. You said, I forgot completely how the strain energy and kinetic energy of a bar can be computed. I will be more than happy to go over on a separate page. Is it okay? Huh? You are gazing at intensely, so you are confused?
No, I'm fine.
Oh, yes. Okay. All right. So, and then the external energy is something we already know. I forgot to explain that. That is, this one is the external energy, the virtual external energy is a force. This is really that. Okay? And that's a force, and that's US. You can use any other symbol you want. You may want to use. Okay. Not only that, we have the discrete mass. Okay. Remember. There's continuum, there's a spring, there's discrete mass. And that discrete mass the location where this coordinate is set US. So this is half m times half mv squared. mv is over here. Potential energy of spring is, if I take that U, this is U at L, this is U at 0, which is 0 because it's fixed, and that's at the edge of the bar, which is this guy. This is the spring. So when the spring is squeezed, it's half kx squared, where this x is US minus UL. Now, please notice that I keep arguments, both the space and time, on the continuum displacement. Because in continuum, U is no longer just a space in dynamics. It's a function of a space and time. Okay? So instead of UL, I put UL comma T. The T is still not specified. Then the Hamilton's principle is total kinetic energy minus total, the potential energy of a bar, potential energy of a spring, and virtual work done on the bar, and time definite integral is equal to 0. So this is a mixture of very simple continuum bar. Of course, when you discretize this guy, you can discretize it at one spring. Now, I want to say a little bit physics about it, since I intentionally made such a small, 10 or 12 pages today. So some of you might say, you'll finish in about 20 minutes today. I want to talk about a little bit the difference between discrete and continuum. Okay? Okay. Okay? So, let me just flip over the same problem like that. And this is, we had a US, and this is the point of the U, LT, and this is the same thing, ULT, and this is a U, GOT, which is a 0 to the, for all time, when it's fixed, it's 0, and the length is L. Now, if I look at this problem, this is a single degree of problem, right? One mass. How about the continuum?
Isn't it sort of infinite?
What?
Isn't it sort of infinite?
Yeah, it's infinite. The space problem, infinite dimensional problem. The reason is a continuum means literally continuum of small, infinitesimally small number of modes. What does that tell us? It's got infinite degrees of freedom, even though equations are only one. There is only one equation. Now, remember what I said in the first lecture says, no mass, no equations motion in this class. Okay? So there are infinite number of mass, there are infinite number of equations, but when you look at, we will see there's only one equation, which is a continuum equation. What that means is that continuum equation has in terms of vibration, infinite number of frequencies, which we will learn, okay? About a little halfway through of this course. In fact, in about four weeks, we're going to start learning the vibration of a continuum bar. So the notion that, well, in my undergraduate, I used to model this guy with the one spring. If you model with the one spring, you are capturing approximately one mode, because there's only one frequency. Now, if you model with the two spring, generally it's better than one model, right? And you will have two vibration mode and two mode and mode shapes. If you model it to 4, I'm going to skip 3. I'm going to have 4 equations, right? There are 4 mass, so I'm going to have 4 equations, right? And I will have a 4 vibration mode. So you can see this guy could go forever. I mean, okay? Now, that's not the end of the story. In static cases, if I apply the load over here, okay, you have a solution, one solution for this guy. You have no more than one solution. Okay? So if this static, I'm sorry, you know everything. The static. Now in dynamic, this forcing function is certainly a function of time. And depending upon the frequency component of this forcing function, at each, if you freeze the time at each frame of time, you have a solution. The infinitesimal delta t later, you have another solution. Infinitesimal time after that, you have another solution. So you can see solution of a dynamic time evolution solution is infinite number of solutions relative to static problem. And this is where the real theoretically as well as a practical challenge in dynamics problem. Okay? And this becomes a much more complicated if this guy is a nonlinear bar. Okay? So for T1 plus delta T plus T1 plus 2 delta T, solutions change. Okay? Whereas there's only one solution. Okay? And this is why even simple vibration of a bar, continuum bar, is not as simple as just a continuum bar for the static solution. Question at this point? Yeah.
Sorry, what does that equation say? T1 plus delta T plus T1 plus...
This is the time history of, say, U at any point. At any point over here, you pick any point in continuum, this guy will have different values for different times.
Okay.
Right? Yeah. Is that clear?
Yeah.
Okay. All right. So I just want you to see there are 3 things in here in this simple chart. In discrete cases, if you decide the number of mass, that's the degree of freedom. In continuum case, there will be infinite little infinitesimal mass, and each mass is associated with its own unique dynamic characteristic. when you look at the entire system for n mass, because in reality, you can get the continuum solution or approximate discrete solutions. The more approximations, degree of freedom you throw in, the more degree of freedom you have to approximate continuum, the more vibrational characterization you are infusing into the system. And this is the challenge of modeling continuum problem or in general structural problem in the dynamic cases by finite element method. Okay? For example, for those of you who took a finite element course, if you use a cubic Hermite shape function for elementary beam bending, you get an exact solution. Okay? You cannot do that here. If you put the one bar, one element, cubic shape function, and approximate the beam by one element, you are throwing out baby with the bathwater. Just give you an example. Okay? Because there are much, that gives you for plane beam maybe 2 or 3 modes. Okay? That's not going to be enough. There will be a lot more modes. Okay? So you see the difference between approximating the simple beam by 1 or 2 finite elements vis-a-vis 1 or 2 finite elements for dynamics problem. You need many, many more elements to capture some first 5 mode or 10 mode of the beam vibration mode. Okay? Okay. So we are back to where we are. So let's move on to next page. Okay. Here I kind of wrote down the final shape, but let me work it out here on the side. This might be a little bit too abrupt for now, so let me just take a, I have half an hour, so I can do that. So, so this one is a double integral, okay? That's number one. It's strain energy, kinetic energy is computed, how do I do that? I forgot. Okay. Let's do it right. So this part is finding out the strain energy. That part is coming from Hamilton's principle, time-definite integral. Remember for the discrete case, we did a similar thing. In this case, we are only using lumped mass and velocity at that point. Okay? In a continuum cases, what we have to do, this is not true. This is T, I'm sorry. We get the total kinetic energy for each of those infinitesimal small segment of a space, and then we do the time-definite integral. Okay? All right. every time I do that, I realize I lose. Sorry about that. So what we do here is we do the following for this part. For this part, what we're gonna do here is we're gonna do the time definite integral first. We're gonna flip integration process. For small mass at arbitrary points. And this is u xt dot. We did the time definite integral for one infinitesimal particle at a cross section. Okay? Like that. So then I'm going to apply variation. And variation first. The variation and differentiate, the integration are commutable. So I go all the way down here. In other words, variation of integration is commutable. You can write this way. Okay? This commutativity. And I can take all the way from here to there, and finally I can walk over here. So once I do that, then I have a little bit kind of, then the half m is out. I will walk u dot square. Dx, and this guy is if I go through that, I will have m u dot delta u. That is delta u dot square is delta u dot u plus u dot, delta u dot, which is a 2 u dot delta u dot. So the half goes away, and I have u dot delta u dot dt dx. Now, this one, in other words, is the same form. AdB is AB, definite integral, minus B dA in that form. So I'm gonna apply this one. When I apply this one, I will have the following form: M u dot delta u. This one is the same as this guy. T1, T2, then minus M. I'm going to differentiate this guy once, which is that one. And I have a B is delta U. It's a little bit busy, but you can follow, right? Okay? So this, if I specify delta U at the T1, T2, this guy goes away. Okay? And you are left with this one. And that is exactly what this guy is about. Here, I'm sorry, I changed to M2 row, but it should have been M. Okay? So we took care of that part. This part goes exactly the same way. In this case, we perform special integration first. Okay? And let me go through that in the next page.
Question?
Yeah.
You said that if you apply the boundary conditions, that
I haven't applied boundary condition here yet.
Okay.
Okay?
You're gonna get to that.
Yeah, we're gonna get to that by working out this guy.
Okay.
Okay? You are a little ahead. Okay? Now, I'm gonna do the same thing. Where this thing came from. This thing came from in this case, we carry out special integration first. In the kinetic energy, we carry out temporal integration, definite integration. Here, we're going to carry out this guy, same thing. So that one is the same. We're going to use a ux, these two guys. And if I perform variation, I'm going to do the perform variation over here. And that one is exactly 2ux delta ux. Okay? So I'm going to substitute that guy. Okay? Now we're going to use exactly the same formula in the form. That is AdB, definite integral, say A to B is AB minus P dA. Okay? So we're going to use this integration by part. Okay? There's no magic, right? So what we're going to do, I'm going to do A, in this case, ux, P delta ux. So I have here is ux delta u 0L, okay, minus integral. I'm sorry, I'm missing here EA. This guy is uxx because that's TA is. So that's like TA in that formula. And delta ux and tx. So let me use a different color here. Okay? This term goes over here because it becomes minus because you know delta t minus delta v. So that minus cancels and you get the positive. Okay? So this term, and you have, I'm sorry, shouldn't be delta ux, delta u. Okay? Delta u. Same thing with the kinetic energy. This guy was mx. Okay? Now let's come down here. Okay? And let me use a different color. Make sure that we are doing the right thing. Okay? So this guy times delta u is the integration at L. This times that comes from here. Then minus part, this minus part comes from at 0 over here. Let me use different color. See what I can use different. Is there a different color? Yeah, yellow. So this integration is minus over there. And this is 0 part. And that is x equal to 0. So this term, that term, this term came from all of these. It's complicated, right? I have to admit. Kinetic energy was very simple. Kinetic energy was just that. Because u dot delta u T1, T2 is 0. Because when u is specified at time T1, T2, remember? Last Thursday? Okay? So the delta u x T1 is 0, delta u x T2 is 0. For arbitrary x, okay? Once you specify T2, okay? The variation of springs, we did it, okay? We did it, so that's outside of continuum part. Now let me clear that out and repeat one more time. Ooh. Repeat one more time. Again, I'm sorry. This one came from like that. And then this one, that one all came from here, okay, and then let me say all this and all this came from essentially delta half mus dot square minus half K and U L T minus US T squared. All this 1, 2, 3, these terms all came from that one. Now, there is some benefit which we will go through this. We will go through this one more time in 2 or 3 lectures down the road, because as much as I have higher hope on you guys' intelligence, this can be confusing, so it's worth repeating. Okay. So when you look at this guy as a totality of this term, there are 2 terms. There are this term, and there are this term inside the time indefinite integral, and this one and that one. There is these 2 terms, delta u xt x equal to L, and delta U xt x equal to 0. Okay? This term and that term. Okay? And there's a bracket inside. So let's look at the boundary condition of a bar all the way back over here. So for example, if it's a fixed, no matter what the time, u 0t is 0. Therefore, delta u 0t is 0. Okay? And this is one boundary condition. And this you learn in your the continuum mechanics course as a what? Is it natural or essential boundary condition when displacement is specified? So only 5 weeks you forgot?
It's been about a year.
Is it about a year? There are 2 boundary conditions, right? Okay? Right? One is essential, one is natural, right? And or one is kinematic, the other one is as a von Neumann boundary. One is a Dirichlet boundary condition or von Neumann boundary condition. I don't know what phrase you are instructed to use. Dirichlet and von Neumann? Okay. So this is Dirichlet or von Neumann? Dirichlet. Okay, this is essential boundary condition. Essential means kinematics. So when you identify boundary condition, you look at kinematics first, geometry. When the geometry condition, you cannot find boundary condition from geometry, that's when it becomes a von Neumann boundary condition or a natural boundary condition. It's there. So in this end, this is the 0. Over here at x equal to L, this guy is connected to the spring. So you really don't know the displacement at the end of the bar, right? So therefore, this guy is non-zero, and this guy is 0. This guy is non-zero. Because you really don't know this guy is moving around, jumping around all over the place. And this is where the von Neumann boundary condition, or natural boundary condition. So this guy is 0, okay? And this one is related to the forces at the support. So this guy is 0. In this case, this guy is non-zero. Therefore, this whole the expression have to be 0. And that is what you get boundary condition. In other words, if you go through Hamilton's principle, you get boundary condition automatically given to you. You don't have to search for it. Okay? All right? Therefore, what's left is these 2 guys. And these guys are arbitrary inside the domain. Therefore, in order for this guy to be 0, this has to be 0 because US is independent variable from continuum variable. Okay? Over this guy. Therefore, this expression has to be 0, and that expression has to be 0. So let me clear that up. So, yeah, we still have time. So this one is 0 due to essential. This guy is a non-zero, natural. Therefore, this one is gone no matter what. This guy is a really reaction force, but we don't need to worry about it. So therefore, that has to be 0. And this is, we don't know. Therefore, that has to be 0. And this is arbitrary, so delta U is non-zero. Delta US is non-zero. So this guy has to be 0. So we get essentially 2 equations, which is really governing equations. Boundary condition, which is von Neumann boundary condition, and Dirichlet boundary condition. So we have 2 boundary conditions and 2 equations motion. So in other words, if you do this thing, you get the boundary condition as a part of the variational process. Whereas in classical continuum mechanics, you gotta look for it. You gotta identify it. And that is not trivial. Okay? So we have 2 governing equation, 2 boundary conditions. One thing I want to say from the outset, even though this guy started with the continuum bar linked with the spring, notice over here, there's no discrete spring, there's no discrete mass appearing in continuum governing equation. This is very important because no matter how complex discrete spring mass damper you put around throw around the continuum equation doesn't care. The governing equation is dictated by interior equation of the continuum. Where does it come? Where does a discrete spring mass come? It comes in the boundary condition. So any discrete mass damper spring attached to the continuum, they behave like a boundary condition on the continuum. Okay? And in this case, this is a typical, just all stat. Except the X here is actual spring shortening or lengthening, okay? So if you want, you can see here immediately. Like that, which says this guy, the spring attached to the continuum, is modeled like mass-dominated cases. Mass-dominated cases. Remember, for the mass-dominated case, we have a spring. Okay? For the spring-dominated case, we have a mass times acceleration, ground acceleration. So you can view that this guy it's like in our single degree freedom UG ground. Okay? So you can see right away when you do all these elegant terms, in this case, when the spring is attached to the mass, the continuum, the spring mass system acts like a mass-dominated system. So what we discuss in single degree freedom, the physics comes right into this. Okay? And this is the Dirichlet boundary condition. This is the von Neumann boundary condition. Von Neumann boundary condition, let me explain this and then we will finish today and maybe continue the rest of the thing today. this one is essentially A times sigma, okay, which is a force. So this guy is acting over here at the end of this part. This guy is essentially force acting this way. Okay? Now on the spring, okay, on the spring over here, we have this guy as a positive, okay? But if I write this guy, instead of that one, I write US minus ULT, okay? Then this means this is US, and this is UL. This is continuum. So that is force really acting in this way. Since this guy is a minus of that, this guy is actually not this direction.
Blackboard never does that.
Sorry about that. This guy is that force. Okay? And this guy is essentially this force. So this one says some of the stress due to the continuum, okay? And the spring force at that junction, some of them are equal to 0. And this is, if this one was not the nice problem like that, but suppose you have a block of a bar like that, okay? And there is a spring mass hitting over here up and down. This, what it says is, here's the impact force is equal and opposite. That stress and times the area is average force, right? This average force is exactly opposite to the spring force acting on it. Okay? So if you really dig into simple problems, there are a lot of physics we can actually appreciate. Okay? And this all is happening. Remember, this guy is a function of time. It's all happening at an instant of time. And this is satisfied all the time. Has to be. Okay? And let me just take one more shot and see whether I can take it there. So we just finished the right on the time, because that's all I wanted to do today. The 5 pages, okay? And 5 pages has a lot of things in between the lines, okay? And the homework is due this Thursday, right? Or today? Today, where's the homework? So I'll try to go a little slowly and touch on the relevant part of the homework so that
Get our next homework stuff? Or first homework back?
the first homework